SwayamPrabha. Digital India. Educated India.
Hello everyone. So we were talking about modeling and simulation and the cost associated with it. We ended with this slide in the last class where we talked about how the time taken to perform a DNS of homogeneous turbulence, how it increased with increase in R lambda, the Taylor scale Reynolds number. So essentially it was a function of R lambda to the cube, or REL, R lambda to the sixth, or R lambda to the cube. And as you can see here, there's a plot shown with TG in number of days shown on the y-axis and R lambda on the x-axis. The circles there, the symbols there represent actual data from computations, and the line represents the fit on using those points. The solid line is estimated from the equation that was shown earlier. If you remember, the solid line is represented using this equation here. And the dashed line is based on DNS timings. So symbols are from DNS timings for a 40 node IBM SP2. Obviously, if you have a faster computer, you're going to get much better timing. The solid line is the estimate from the equations, and the dashed line is the asymptote R lambda over 70 to the whole thing to the power of 6. So as you can see, the time is increasing significantly, and it is increasing drastically as a power of R lambda. And the symbols represent the fact that you're only able to get timing, at least until the plot was generated. You're only able to get timing until an R lambda that is much less than 100. So that was all we could do. But in today's day and age, obviously, you will find calculations of R lambda that are beyond 100, that are close to 1000. So you will find data points in here, somewhere in here. And I'm going to assume that you're going to find points that are close to this line. It's not going to be very off from that because the timing kind of matches. Now, obviously, with different computers, you will have slightly different, the exact fit is not going to be followed. But so you will have slightly the points that are slightly deviating from this line, but it's going to be in and around that line. But the point we're trying to make with this plot is that a significant cost is incurred significant cost is incurred for DNS, and it increases significantly with increase in Reynolds number. So low Reynolds numbers is okay, but as the Reynolds number keeps increasing, and which it would do as you get to more and more practical flows, isn't it? And so as the Reynolds number keeps increasing, the timing is just drastically increases, and it becomes very hard, very impractical to conduct a DNS of very high Reynolds number flows. Although in today's day and age, it is much more practical than it was 20 years ago, 30 years ago, 10 years ago even. Okay, so this is a plot showing, and we'll describe this plot in detail. This is a plot showing how the wave numbers are distributed across the different range. Now, as you can see from the plot, you are seeing the energy containing range, you are seeing the inertial subrange, the dissipation range, so there are some insignificant modes are there. So what does this mean? So first of all, when we try to assess the cost associated with DNS, we were saying that the maximum wave number is at kappa max, isn't it? The maximum wave number is at kappa max, which is the maximum wave number in one direction. So so you will have kappa max in both directions, meaning what I mean to say is it is 0 to kappa max, but the actual wave number is from minus kappa max to kappa max, or 0 to 2 kappa max. Those are the maximum wave numbers, right? So 2 kappa max is the maximum number of wave numbers in each direction. So that means you have a spherical space where you have 0 to kappa max, 0 to kappa max and 0 to kappa max in the 3 different directions. Are you following me? So earlier when we wanted to find out the wave number magnitude, it was equal to kappa 1 squared plus kappa 2 squared plus kappa 3 squared. This is very important. This whole concept is very important. I have explained the whole idea of wave number magnitude multiple times and why you get a so-called spherical wave number space. Now when you calculate the wave number magnitude, you are getting square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared, which is basically the radius of a sphere. Kappa 1, kappa 2 and kappa 3 are the wave numbers in the x1, x2, x3 directions respectively. And the wave number magnitude represents the radius of that sphere made up of the kappa 1, kappa 2, kappa 3 wave number space. So that spherical space is what is shown on the screen. Now since we are showing it on a slide, we are showing it as a circle. Follow me. So on this circle, it is 0 to kappa max is your minimum to maximum radius. Yes, 0 to kappa max, which is basically going to be the wave number magnitude. And the maximum wave number magnitude is going to be made up of kappa 1, kappa 1 max and kappa 2 max and kappa 3 max, the square root of each of these squares added together. Now think about it. You are going from a cubical space, isn't it? Homogeneous turbulence is done in a cube of size L, and you are dividing it into multiple wave numbers, isn't it? You're dividing it into multiple wave numbers. So each direction you divide it into wave numbers corresponding to 2 kappa max wave numbers. In other words, it is from minus kappa max plus 1 to kappa max, right? So you are going in wave number space, it is cubic, but the only wave numbers that matter are the wave numbers in the sphere. I hope you're understanding this. Our physical space is a cube, which has a side L, and this physical space cube is now you are using this physical space cube and discretizing your wave numbers into 0 to 2 kappa max wave numbers, right? In magnitude, it is 0 to 2 kappa max wave numbers in each direction. But that you are dividing it in, you are taking only the sphere because your wave number magnitude is equal to square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. So essentially, you will just have a sphere and everything on the outside is insignificant modes. This is the sphere within the cube. This is the sphere within the cube. So you have this outside area, outside that sphere, but still within the cube. That is, those are insignificant modes. Because the only thing that matters, you are only considering the wave number magnitude, which is square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. So that is why you are only getting a sphere. I hope you are following me. So a little bit of explanation is there in the next slide. So in 3D wave number space, the modes represented lie within a cube of side 2 kappa max, isn't it? In wave number space, it is 0 to L, but in wave number space, it is 0 to 2 kappa max. So if I look at this, so remember this one, L, kappa max is pi n over L, isn't it? Kappa max is pi n over L. Your wave numbers go from minus half n plus 1 to half n. And your kappa max is half n kappa naught. So that is only one side, isn't it? That is only one side. But your wave numbers go from minus half n plus 1 to half n. The kappa max is half n kappa naught. But the other side is there. So that is minus half n plus 1. So essentially you have two kappa max wave numbers. You have two kappa max wave numbers. That is what we are trying to say. So the cube is made up of two kappa max wave numbers. That's what we are saying. And in a well-resolved simulation, only modes within a sphere of radius kappa max are dynamically significant. Why? Because only that radius matters. The radius is square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. And that is what this radius is, right? This is kappa max, the radius of the sphere, which is equal to, where that radius of the sphere is equal to square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. So now, with that as the background, now let's look at the different ranges. If you think about the dissipation range, the dissipation range is starting all the way from the last wave number, right, to something like kappa di. Everything in between is the inertial subrange, all the way until this small circle that you see here. And I'm going to erase it so that I can draw on it again. But it is that small circle that you see there, that is your energy containing range. Anything in between is the inertial subrange, ISR. This is the dissipation range. And that small dot that you see here is the energy containing range, ER. You understand what I mean? So that small circle you see there is the energy containing range, where most of the energy is produced, where production happens. Then, so there is this energy demarcation length scale, or the energy demarcation wave number, that is marked by that circle there. The energy demarcation wave number is the radius of that smallest circle there. The dissipation range demarcation wave number is the radius of this second smallest circle, or the second biggest circle. And the Kolmogorov scale wave number, the Kolmogorov wave number is your kappa max, because that is where you will have it fully resolved. So that is the radius of this large circle. So this we have drawn it according to scale. So your energy containing range is kappa less than, energy containing range is kappa less than kappa EI, isn't it? And your inertial subrange is kappa less than kappa di, but greater than kappa EI, isn't it? Greater than kappa EI. And your dissipation range is kappa greater than kappa di, or less than kappa eta. The kappa eta is going to be the largest wave number that is resolved, so that your Kolmogorov scale is resolved. I hope you are understanding this. So that is how we are defining this. So we defined this cube, then we got a sphere out of it. Everything outside the sphere and within the cube are insignificant, because all we are interested in is the radius, is the wave number magnitude, is the radius of that sphere. So everything outside the sphere is going to be insignificant. Now, here what we are also saying is that we have this small, really small circle, a slightly larger circle, and the full circle. Three circles. The first really small circle represents, well, it is associated, it is corresponding to the radius associated with the energy containing range. The next big circle is corresponding to a radius associated with the inertial subrange, kappa di. And the largest circle is corresponding to the radius associated with the Kolmogorov wave number, kappa eta. So what is shown here, I was saying earlier, this is according to scale. So the inner sphere of kappa E corresponds to the peak of the energy spectrum for isotropic turbulence at R lambda equals 70. That is, at higher Reynolds number, this circle is going to be even smaller. Even smaller. because this is at R lambda is equal to 70. We have hardly touched very practical Reynolds numbers at R lambda equal to 70. So you can imagine as you go to the much higher Reynolds numbers, the separation between the smaller scale and the larger scale increases, so that the smallest circle that you saw in this plot is going to get smaller and smaller relative to the largest circle. Following me? So essentially 99.98 of the modes represented have wave numbers that are larger than kappa di. 99.98% of the modes. That means 0.02% of the modes represent motions in the energy containing range or in the inertial subrange. That's it. 0.02% of the modes. 99.98% of the modes are in the dissipation range. So the entire DNS calculation, or I would say most of it, 99.98% of the cost is associated with resolving the scales in the dissipation range. You have to ask the question, is it worth it? Right? It is true, it is good to be aware of it. The fact that you are spending almost all the modes, right? 99.98% of the modes. That means if you have 100 modes, only 2 modes are associated with the energy containing range and the inertial subrange. Only 2 modes are associated with the inertial subrange and the energy containing range. 98%, right? In fact, more than that, I would say, right? Not just 2 modes, right? So more than that is associated with the dissipation range. So you are spending most of the cost on the dissipation range, on the scales associated with the dissipation range. That means a significant cost is associated with trying to resolve the very small scales. So that is why approaches like RANS and LES became so popular. Because one might ask the question, if you're spending so much time, CPU time, computational time on the small scales, is it really worth it? So can't we just resolve all the large scales and even the inertial subrange and try to get means out of it, try to get filtered scales out of it, and maybe we can get meaningful statistics out of it, rather than spending a lot of time trying to resolve the small scales and not getting as much benefit. That is where the RANS and LES comes in, and that is why they have become more popular, because for a fraction of the cost, they are able to get a reasonable estimate of the flow. When I say a reasonable estimate of the flow, the means, the variances, they are able to give that. Okay, with some error, yes. However, it is important to understand that DNS is unparalleled in accuracy. You want to say that you are doing the most accurate calculation possible, you have to resolve all the scales and you have to do a direct numerical simulation. If you're not doing that, at least you have to be aware that this is all you're resolving, this is what you're modeling, you're not accounting for these scales, you're only accounting for these scales, so you're bound to get some errors and you have to deal with it. I hope you understand this. So that takes us to inhomogeneous flows, because so far what we've been doing is related to homogeneous turbulence. And I was saying earlier, the reason why we picked homogeneous turbulence is because it provided a very simple framework in order to assess the cost, in order to assess the accuracy, in order to assess all these different aspects which we could not do so easily for any inhomogeneous kind of flows, like for channel flows or for pipe flows. So what we could do, for instance, when we looked at DNS, we looked at spectral methods. Why did we look at spectral methods? Because it is the most accurate approach that is available. It has a so-called infinite accuracy because the truncation error is not there. The truncation error is absent because you're not using a numerical method that has a truncation error, isn't it? You're using a spectral method that is the most accurate method possible. Now, there is some limitation to it, and that is the fact that you have to use periodic boundary conditions, because you're converting your Navier-Stokes equations into a set of Fourier series, which means into a set of sine and cosine series, which means you are assuming the flow is periodic. You're assuming your boundary conditions are periodic. So that is that limitation. However, it helps us in assess the accuracy of the method. What we were able to do is we compared that with something like a RANS based method on the other end of the spectrum, like a mixing length model, which was not as accurate, much simpler to use, very cost effective, but not as accurate. And the reason we picked spectral methods is because of its accuracy. Yes, it has its limitation that it is restricted to a certain kinds of flow. So we talked about range of applicability in this model. DNS cannot be applied to all kinds, DNS using spectral methods cannot be applied to all kinds of flows, mainly because of the periodic boundary condition limit. However, we were still able to assess the accuracy based on that. And because we were dealing with homogeneous turbulence, we could write it in terms of the cost, we could write it in terms of the R lambda value. How? Because we could get the energy spectrum in terms of the R lambda value. We could say what is the maximum, the smallest length scale that can be resolved, the maximum length scale that should the integral length scale. All these estimates are easily obtained in homogeneous turbulence. If all these estimates are easily obtained, we can get the cost associated with these problems relatively easily in homogeneous turbulence. If you think about inhomogeneous flows, which is what we are going to be dealing with next, it is not that easy to come up with a Kolmogorov length scale, because it is associated with an energy spectra, and there are multiple complexities associated with those kind of flows. There are, because it is let's say you have a wall bounded flow, you have a boundary layer associated with near the wall. The scale there is going to be very different. Away from the wall, the scale is going to be very different. So the Kolmogorov length scale, estimating the Kolmogorov length scale is possible, but it's not that straightforward. Whereas in homogeneous turbulence, coming up with the Kolmogorov length scale is actually straightforward. You can get a very good estimate of the Kolmogorov length scale. And once you get a good estimate of the Kolmogorov length scale, the maximum wave number that has to be resolved is also obtained. Knowing the integral length scale, you will know the total number of wave numbers that are required to resolve all the way to the Kolmogorov length scale. And this is key in assessing the cost. So we were able to do that because it was such a simple flow problem. The homogeneous turbulence is such a simple flow problem. And by using the spectral methods, the fact that it was very accurate, meaning we did not have to take into account any other aspects of, say, truncation error, because we are resolving the entire flow. We are resolving all the way down to the Kolmogorov length scale. That means if we are resolving all the way down to the Kolmogorov length scale, it is the most accurate. So the wave numbers are what they are supposed to be. So that gives us a very good estimate of the cost. So using that, we were able to come up with this plot, isn't it? What is the time required to in days to run a DNS of homogeneous turbulence on a machine like IBM SP2, which is now obsolete, by the way. This is a machine that was developed more than 20 years ago, which is now obsolete. So the machines right now would give you much faster speed up, much higher speed up using this estimate. So we were able to come up with, okay, what is the total number of days of computation time versus Reynolds number. And this is plotted with R lambda because we are considering the homogeneous turbulence problem. Right? R lambda does not come into play in jet flows or pipe flows. It comes into play only in homogeneous turbulence. So we were able to come up with that. And the asymptote was R lambda over 70 to the power of 6. So it is to the 6th power, and with the integral scale Reynolds number, it is to the 3rd power. So that estimate kind of holds. So in order to get an estimate, you can just take the total number of time in days on a gigaflop machine So that would be the IBM SP2. That would be REL cube. Now, the total time in days would be, if it is, say, if you're getting something like 10 to the 8, for instance, and if you have a machine that is 8 orders of magnitude faster than this machine, the gigaflop machine, 8 orders of magnitude faster, which is what today's machines are, then your 10 to the 8 days would go down to 1 day. That's sort of an estimate of it. That's sort of an estimate. So that is how this kind of plot helps. That is how these kinds of estimates help. And that is what we were able to do. All that being said, we realized in today's class that most of the time, most of that 10 to the 8 days on a gigaflop machine is spent on resolving the dissipation length scale. The scales in the dissipation range. So because this small circle that you see here, that is the amount of wave numbers in the energy containing range. This slightly bigger circle that you see here, that is the amount of wave numbers in the inertial subrange. So what we are saying is most of our effort goes into resolving the scales in the dissipation range. That is the disadvantage of DNS. It's true, it is, however, we need to be aware of it, so that is how we develop new models. So the way Rance and Elias approaches came about is to avoid this kind of skewness where you are spending most of your effort in resolving scales that only account for very little of the energy, but a lot of the wave numbers is associated with it. Hope this is clear. So next class what we'll do is we'll move on to inhomogeneous flows and look at different aspects associated with it. Thank you.